second paper about the use of Cationized cotton to improve the cotton dyeing process. That's Dr. Hauser from College of Textile, North Carolina State University, USA.
Good afternoon. I'm an associate professor. I teach textile chemistry at NC State. I worked for some years in the textile industry before I went to academics, so I think I have an appreciation of the real world. And what I'd like to do today is talk about the use of a product, a process where we catenize cotton to improve the cotton dyeing process. And one thing we should say is, why do people like cotton in the first place? Well, it's a very comfortable fiber. It has good aesthetics. So it's actually the preferred fiber for when consumers are asked which fiber they would prefer to wear. But then we could ask, well, why does the dyeing process for cotton need to be improved? Or what's wrong with cotton? What's wrong with the cotton dyeing process? There is a lack of affinity between the cotton fiber and the dyes that are commonly used to dye cotton. There's no natural attraction between the fiber and the dye. And so what you get is less than optimal dye units. All the dye is not used, does not completely leave the dye bath and go onto the fiber, which means there's color left in the dye bath that's discarded later. In an attempt to overcome this lack of affinity between the dye and the fiber, dyers have used electrolytes like sodium sulfate and sodium chloride. Sometimes as much sodium chloride is used as a weight of the fiber itself. Extended dyeing times and elevated temperatures during the dyeing process are necessary to get adequate dyeing use. This leads to an adverse environmental impact because you have a lot of salt in the effluent, you have a lot of water in the effluent. You use a lot of energy to dye cotton. It's a very energy-intensive process. Multiple rinses and scours are necessary after you dye cotton in order to remove any loose dye that's held on the surface that would cause fastness problems later, which means you must use a lot of water after you dye it. And this also extends to dyeing cycles. It's not uncommon if you're dyeing with fiber-reactive dyes to spend as much time washing the fiber as you spend dyeing it in the first place. So these are things which again leads to low productivity and use of a lot of water and energy. So what can we do about it? How can we improve the reaction and the attraction between the dye and the fiber? Well, one way is to choose our dyes a little bit better. That would develop, in many cases, into developing new dyes. The problem with developing new dyes is that it's very expensive to develop a new dye and to get it approved in today's regulatory climate. So that's a possibility, and some dye stuff manufacturers are going in that direction, developing low salt, high needle dyes. You can optimize your process perhaps by getting different equipment. The problem with that is that new equipment is expensive, and what do you do with the equipment you have already? If you sell it on the market, then you may be selling it to one of your competitors. So you would really rather try to use the dyes that already exist in the dyeing equipment that already exists. So that leaves us with modifying the fiber. If we can put cationic dye sites into the fiber uniformly, we could attract cotton dyes, which are all going through an anionic stage at one time or another during the dyeing process. And then these dyes would be naturally attracted to the fiber. We wouldn't have to use the high salt levels or the high energy at all times to get them to go on. We can use amines if we want, and some people have inserted amines into cotton. Usually, in order for it to have a cationic site, you've got to go to low pHs. Another approach is to put quaternary sites inside the cotton. If we do that, then we've got a pH-independent positive charge on the fiber that would allow us to pick up the existing dyes. So how can we do this? Well, people have tried to modify cotton already with cationic polymers. And what you get is a charged surface, it's a charged layer of the fiber surface with something like this. You have a charged surface, the polymer with the positive charges. Then the dyes can be attracted and hopefully will stay there. And quite a few chemicals have been used for this. Cationic polymers made from acrylates with mazoles, polyamine and chlorohydrin resins, polyamino condensation products. All of these have been used to coat the fiber surface to get a cationic charge to improve the dye attraction. And they have worked for the most part. You get higher dye yields. The dye is used efficiently, just respected. Better wash fastness. The dye doesn't want to wash off very well, so it stays on. And usually these can be applied by exhaustion techniques. The negative, however, is that in almost every case, there is an adverse effect on light fastness of 1 to 2 units. The dye tends to be green dye, or stay on the surface, and is more affected by light than it would be if it was throughout the fiber. So this is a possibility, but it's not the final answer. Another way to approach this is to use a reagent, a small molecule that will penetrate into the fiber before it reacts, and do what I call an internal modification. And we have something that a positive charge will react with the fiber to now have a covalent bond inside the fiber with a positive charge to attract the dyes. And then we have something like this inside the fiber. Then when the dye comes along, it's all the way throughout the fiber. So that's our approach. What has been used and what is available for this? These molecules have been used. This particular one can be used with DMDHE with a pad bake procedure. This molecule also can be used, and it turns out this one is also on one of our posters outside. It's been used in the pad bake. It exhausts some also. This material here has been used in the past, which is a large material. You can see these have a monochlorohydrazine. They do exhaust, but this particular one, they had it reported poor light fastness. We're going to focus on this molecule here, which is a very easily commercially available material. It's used by the millions of kilograms every year to modify starch. Supplied nicely in a pad batch, pad steam, or pad bake process. This is the molecule that I'll be talking about for modifying cotton. What's its chemistry? You make this material by reacting epichlorohydrin with trimethyl ammonia. You then react. Then this molecule is what is commercially available. During the actual application process with hydroxide, you form an epoxy material, which is a reactive species, which will then react with the cotton fiber to form the covalent bond that we have there. And unfortunately, we also get some hydrolyzed material where we have a glycol, so we have an unreactive material that is not attached to the fiber at all and has to be removed by rinsing. We can apply this by several methods, and you can see that the molecule does not exhaust very well, so at low liquor ratios, about 10% effective yield, pad steam, pad bake, and cold pad batch are much more efficient at applying this reagent. In previous work, we talked about dyeing with these fibers with direct dyes. I'm just showing you for some comparison purposes. the color yields with cationic materials, with direct dyes. You can see in every case we get a significantly higher K over S. And this happens to be a turquoise, quite an increase in color. But we also get good wash fastness and light fastness properties. Notice the wash fastness and light fastness in both cases are difficult to read. This is 20 and 40-hour light fastness. So we get the increase in dye yield without the use of salt, and we get good light fastness at the same time. Here is for the direct red and the direct yellow, 106, same thing, very good fastness properties. Fibre reactive dyes, the same general feature is seen. We have higher K over S, which means better dye, better color for the amount of dye that's used. Again, this happens to be a turquoise, quite a significant increase in color yield. Fastness is quite good for all of these reactive dyes also. We show some photomicrographs here that shows that this is conventional cotton dye with blue 203. Cationic cotton dye with conventional, same concentration as blue 203. Notice it's darker. Also, the fibers are dyed uniformly. So we do not get ring dyeing with this type of procedure. We get uniform dyeing throughout the entire fiber. And we show the rest of the wash fastness data. We did some work with natural dyes, comparing it to a process where they use mordants with natural dyes. In our case, we simply modified the fiber but did not do any mordants at all. You can see better or equal color yield in all cases. The fastness is much better for this modified fiber. Logwood matter, significantly better. Saves not only in wash fastness but also in light fastness. We also have done this work with vat dyes. Conventional vat dyes require 15 grams per liter of salt and you rinse many times. We took cationic cotton, dyed it. Same time, we did not use any salt and we only rinsed it once after it was oxidized. We got quite good color yields, as you can see, much better than the conventional. Wash fastness, light fastness was quite good. The crock wasn't quite as good, but if we usually you have after scour vats, and we didn't do that in this case. I think that would improve it. That yellow was quite good. So we're getting better color yields with less water, less scour, and no salt in the vat. Sulfur dye, similarly, conventional treatment, 25% on weighted fabric salt, and typical reducing agent procedure in oxidizing it. With cationic cotton, we do the same, a similar procedure, however, no salt, less dyeing time. We did not soak, we just rinsed. The bath were clear after dyeing. Comparison, significantly better color yields for sulfur black, blue, red, and a yellow when you use a cationic dye rather than the cationic fiber rather than the conventional fiber. Color yields are, wash fastness is quite good. We're not particularly pleased with the light fastness here on some of these. It's possible that we perhaps need to modify our dyeing procedure to try to increase the increase the penetration of the dye stuff. I know the fiber is well uniform, but it's possible the dye is striking too fast, it doesn't have a chance to penetrate inside. Same thing with the red and yellow. Still quite good, much better wash fastness in crop, slightly worse on the light fastness. In summary, we've shown that we can effectively increase fiber dye affinity with existing cotton dyes and existing equipment by modifying fiber with cationic reagents. We get better dye yields, better wash fastness, and we use much less water and energy in the process. We generally do not adversely affect light fastness as opposed to prior results with other type of reactants. We think that's because the reactant penetrates the fiber before it actually reacts. And so we believe we have a very efficient process that needs to be considered by industry. I should mention that this is not the first time this process has been looked at. It's about 30 years old. It was talked about in the mid-70s. I think it's been overlooked by the textile industry now. I think at the time, as we heard earlier today about the importance of pollution and cost of pollution and the effectiveness you can do by reducing the pollution, if we can apply processes like this to our cotton, I think we can do an even better job of producing our fiber in an economical and environmentally friendly way. I need to acknowledge the Dow Chemical Company for supporting the research. Clariant and DyeStar presented us with the samples that we used. And finally, the people who did all the work, Adham, Tabba, Ale Balakoma, Kristen Cadden, Josh Sanders, and Helen Mars with the students who provided the data. Thank you.
Any questions? Yes?
Given a lot of cotton nowadays is tending to be treated to make it wrinkle resistant in care, given that these sorts of chemicals also need to bond with RH groups, is there likely to be a competition between these reactive side-producing chemicals and these care finishes?
The question was, if this chemical is used, does that interfere with the easy care finishes? The answer is no. We're doing work right now that will be reported in the fall. And data is in, and actually we get better results. Yes, we get higher increased accurate numbers with the treated cotton than with the untreated cotton.
Yes, please. You say yes.
Yes. Have you ever tried to make it the other way around, which means you dye with direct dye, and after direct dyeing, then you apply cationic dye. So in this case, it gives some brilliance effect for the direct dye.
That we use typically cationic polymers are used in the States to after treat active dyes to improve the fastness, the wash fastness. Unfortunately, the right fastness is almost always hurt by that process.
Yeah, but I'm not talking about cationic agent. I'm talking about cationic dye. So after dyeing with direct,
go back
then you dye again with cationic.
You would have to make sure your shade was matched very well.
Yes, that's right.
Well, excuse me. You're saying that you have to add cationic dyeing sites to increase affinity. I'm speaking from another concept about the planarity of the structure of the dye stuff itself. You know that van der Waals effect has a big effect to increase the affinity of the dye. So can you correlate this also to increase affinity in your
yes. What I was trying to do is allow the manufacturer, the dyer, to use existing dyes with existing equipment. I know that the dye stuff manufacturers are working all the time on improving it from their end. I was looking for something that a company could do today or tomorrow with existing equipment and existing dyes that would make them not dependent on the dye stuff manufacturer to go with it. Yes, it is possible to modify dyes. People have come up with cationically modified dyes. Dr. Lewis does a lot of work at Leeds, modifying dyes and modifying fibers. But in almost every case, he has problems with light fastness. We're getting this improvement without any negative effect on light, which I think is important. Yes, sir.
What is the amount of the textile product you are using compared to dye stuff? This quaternary soap, quaternary product.
Yes.
You are using the same amount as the dye stuff, or depends on the amount of dye?
I understand the question. Typically, for a 2% dyeing, we're using about 5% of the reactant. But you've got a molecular weight difference and everything, so and the dyes are much pure. So
because for the active dyes, for example, you can exhaust Now,
Mhm.
the bifunctional
Yes,
acid dye,
yes,
you can exhaust more than 80 or 85%.
yes, that's correct.
Then you are leaving only 15%
That's
which
correct.
can be removed by washing. Then if you are using your material, you are fixing that
Yes,
that portion
yes, sir.
because the reactive itself is very, very strong
Yes.
against washing and so on.
Mhm.
And so you have only 15% which has to be fixed by the reactive or
Right.
your reactive
Yes.
quaternary salt.
Yes,
The same, you can use, of course, acid dyes.
yes, yes, we
And
have,
that is dyed.
we have some done work, we have reported work with acid dyes on cationic cotton, and it showed some dyeing results.
In these two cases,
Yes.
the linkage between the dye and the quaternary salt is a type of salt linkage
Yes.
through the sulfonic groups.
Yes,
And this also, I think, by soaking, can be removed as any acid dye. If you are boiling an acid dye or whatever, be it
Well-
with wool or with cotton, it will be removed. So the fastness, washing fastness, perhaps you made it only at 60 degrees, but if you can't boil or soak.
okay.
In this case.
Yeah, this wash fastness that I reported was the AATCC 2A wash,
Ah.
which is the common American wash, about 120 degrees Fahrenheit. So it's much lower than,
It's not
right,
salt.
and we have not
It's not
looked at,
salt.
we have not looked at the European high temperature washings yet. We've only looked so far at the US washing, because there's a trend toward lower and lower washing temperatures,
But
especially in the United States.
What about the economy of the process at home? As a whole, the process, because you are using this quaternary salt, then it is a process, and you
Yes.
are paying for that. And
Yes.
for the material itself.
Right.
And
Yes.
then you are dying as normal. So you are doing the dyeing process in 2 steps, not in 1 step.
That is I think I understand what you're saying. This does require an extra step, but I think it could be combined with the preparation step. If you prepare outside of the
Before.
dye. And also, even with the reactive dyes that have 85% exhaustion, you still have to soak.
Ah.
We are not soaping. After the dye bath, the water is clear, it can be used again. So there is still some advantages, even with the dyes that exhaust nearly 100%.
Thank you.
Yes.
Thanks, Hauser.